They're so busy, it's crazy. Ask it over schedule.
Uh, 12:30 sharp. We have to, you know, I was looking at the lectures from last year. I have no idea how fast I went last year, but we're like 5 lectures or something behind schedule because I covered lots of introductory material. But I don't feel any pressure to sort of accelerate because at the end of the day, there will be a continuation of this course, and whatever is not covered, we will do it in another course. All right. So, but I do need to cover 60 slides today. Okay. All right. So the first thing, I think we already discussed the definition of the covariance. So let's assume that we have 2 scalar random variables, x and y. Okay. Maybe I need to point at this one. So they're both scalar. So definition. First of the joint probability distribution is defined with this nice equation, and particularly the first part. You remember when we started talking about probability, we can discuss about probability of events. So if we have probability of random variables x and y, we define this through the probability of events using this first part of the equation, which says that the probability of x belonging in A and y belonging in B is really the probability of events through x and y are mapped on the domains A and B of the real line. Okay, so nothing basically fancy about that. And what is new is, since we talk about the joint probability of x and y, we now define the joint density as nothing else but this integral over the domain of A cross B of pxy, dx, dy. Okay, so this is really old stuff, and this is the new definition of the joint density. Let me define the same way we define independence of events. 2 random variables will be called independent when Px of y is P of x, P of y. So P of x is really the marginal of Px and y, and Py is also a marginal of Px and y. And what I will emphasize today, the independence relation that involves densities, not expectations or anything like that. So it's a really a very strict requirement there. It involves densities, okay? And I say this because we will see shortly something that can get a little bit confusing, that is a weaker statement than independence. All right, so this is about the covariance. So the covariance of 2 random variables is defined basically as the expectation of x minus the expectation of x times y minus the expectation of y. Okay? That's a definition. And if you actually expand this, you can see immediately that's an alternative expression. The covariance is the expectation of x times y minus the expectation of x times expectation of y. I mean, I will use this expression because in most occasions when you need to do algebra, this will lead you to this, and then you continue from there. Okay. So let me give a few more definitions. They are mostly useful for those who play with data. So the first definition is what I call the correlation coefficient of x and y, and it's nothing else but a normalized covariance. So if you take the covariance and you divide by the standard deviation of x times the standard deviation of y, you come up with a new entity that's called the correlation coefficient of x and y. And here is a reminder of the standard deviations, okay? And sort of in the same category of definitions, if you have random variables x and y, you can actually center normalize them the way that you see here. So you remove the mean and you divide by the standard deviation, and the reason you do this is because all of these variables then they have 0 mean and variance equal to 1. I believe in one of the homework problems, the teaching assistants are asking you to do some task with center normalized random variables, and is asking you if there is any benefit actually using those rather than using directly x and y. Okay. So obviously this definition that we have used here, you remember when we had a random variable x, I also introduced the variance of a function of x this way, and actually you can do sort of the same expansion where you define covariance between functions of x and functions of y, and I don't show you that equation, but you can generalize that as well. You may ask me now, what does this covariance between two random variables x and y captures? As we will see today, and I believe in one more lecture, it covers, basically tries to model how x and y vary with each other linearly. The word linearly there, it's important because if you have lots of data that they're sort of are coming from some nonlinear manifold, this concept of covariance and correlation that we will see is not very useful. Okay? So the covariance captures the linear dependencies between x and y, and I'm going to show you pictures basically to convince you today that that is indeed the case. So if you use this definition and you take the random variables to be independent, so if you expand this expectations with the integral of x times y times p of xy dx dy, and you do the same thing here, and you assume independence of x and y, then you can see the covariance is 0, and in that case we say that x and y are uncorrelated. All right? So independence implies that the variables are uncorrelated. The other way around is not the case, because if this is 0, this is a relation that involves expectations, and the independence involves probabilities. It's a much more rigorous statement. Okay? So being uncorrelated does not mean you are independent. It's very important. Okay. So this is the definition of uncorrelated. If the covariance is 0, we say they are correlated. If they're independent, I already stated, you know, you can do the algebra, it's trivial, then the variables are uncorrelated. You may see this in textbooks and papers. There is another definition of relations of x and y. We call x and y to be orthogonal if the expectation of x times y equal to 0. And in that case, basically, this looks like the Pythagorean theorem or something like that in terms of expectations. So remember, this requires this orthogonality condition that you see there. Okay? I don't think we will use it in this course, but just keep in mind that's sort of another definition. All right, so let's make life a little bit more difficult. We discussed about random variables that they're scalar. So now I have a vector random variable. Okay, so this maps events to Rn. Okay, so we're going to define this cumulative distribution function of all the variables x1, x2, xn. All right, these are all the variables in the vector to be basically the joint probability of arriving from the joint probability of x1 to xn. So the CDF is basically the probability that capital X1 is less than x1, capital Xn less than xn. Obviously, the CDF is between 0 and 1. And if you want the density, effectively you define, if you use the CDF, the density basically is the nth derivative with respect to all the variables. That will give you the density. So if you integrate basically the density on the variables x1, x2, xn, you'll be able to calculate the probability in the joint space of x1 to xn. Again, nothing sort of fancy, but this is a random vector basically, and you can treat of this nothing else but a collection of scalar random variables, but we don't treat those variables as independent. You have to work with all of them all together. So the expectation, nothing new. I by mistake or intentionally have not denoted these vectors with, I should have put this capital X as bold and this little x as bold to emphasize their vectors. but effectively you see in the integration, the expectations again, integral of x px dx, but the expectation, because x is in Rn, so you integrate this in Rn. You can define marginal expectations. So if you only want the expectation of one of the components of the vector, you just plug in that component, p of x, and can you realize here from this calculation that somehow when you write an expectation of only one component, all the other components you can get rid of them and put only the marginal there? Because effectively this requires integration in x1, x2 to xn. So you integrate all the variables out except xi, so you get back to the classical definition. Okay? So if you are going to write the expectation of xi this way or that way, it's the same thing. Just remember that p of xi is the marginal of p of x, where everything else except xi is integrated out. Okay? So the covariance matrix now, all right? It's a little bit more complicated, but following basically the definition of the covariance of two variables that we had before. The covariance, capital of X is x minus e of x times x minus e of x transpose, p of x dx. So basically the covariance, you can think, because x is a vector, it's really, the only thing you need is the covariance between all possible combinations of components of the vector x. That's what it is. So there's no really any new definition there. Okay, and obviously here you need to have p of x. So if you want the component, the matrix is, you know, if you want the ij component, effectively what you have is xi here, xj there, and of course, you know, similar to what I saw before with the expectations, all other x's, joint xi and xj, you can integrate them out, and there put only the joint distribution of xi and xj. Okay, but keeping it like that, it just makes life sort of more straightforward. A very important quantity, a very important property of the covariance that we're going to be using everywhere quietly, it is that it's a symmetric matrix, right? You can see it. And even more importantly, it's positive definite. Now, if I ask you what's positive definite, you will tell me you forgot. So a positive definite means that if you take any vector that is non-zero, then V transpose times the covariance matrix times V is greater or equal to 0, and it's actually 0 only when V is 0. That's the definition of positive definite. Okay? And that has implications that the eigenvalues coming to be positive and all of these things. But I can tell you, without this property, almost everything we do in this course and every other course in statistics will be useless. This is a fundamental property. Okay? So to prove that this is positive definite, it's very simple. You follow the definition, you multiply with any vector V transpose V. And so I put V transpose, and then I combine things to look nicely. And effectively what you get is, you get a scalar V transpose x minus the expectation of x. This is the expectation of x, by the way. My shorthand notation, so the equation fit in one line. So this is a scalar square times p of x dx. So this is non-negative, this is positive, so you get non-negative. Okay? So the covariance is symmetric positive definite matrix. And, not surprising, if you take, so this again captures the covariance between all the components of x, right? So if you want the variance of a given component, it comes out that it's really nothing else but the diagonal elements of the covariance matrix. So for example, if you take the II element of the covariance matrix, so you take this and you put I equal to j, this is what you get. I mentioned all the other variables, you integrate them out. So what you get is this, which by definition is the variance of xi. Okay, so the covariance in the diagonal basically gives you the variance of the individual components. I'm just writing this in an expanded form, so that these are the variances, what we just mentioned. In this case, the vector is d-dimensional, and these are the covariances, okay? And again, this is a symmetric matrix, so covariance of x1, x2, the same as covariance of x2, x1. And sometimes in applications, instead of playing with the covariance, you play with what's called the correlation matrix, where in effect, you divide these covariances by the corresponding standard deviations. So you transform everything to correlation coefficients. And I remind you that the correlation coefficient of two variables, x and y, is you divide by sigma x times sigma y. Okay? The nice thing with the correlation matrix is that all terms in that matrix all elements are between -1 and 1. Okay? So, and actually, I give you a proof of this, that I want you to read it as a little exercise, because in life nothing is trivial. It's not because I told you that this correlation coefficient is between -1 to 1 that you believe me. So there is a trivial proof that, of course, if you don't know the trick, you know, it may take you a one page of calculation, but here I give you a proof that the correlation coefficient between two variables x and y is actually greater than -1 and less than or equal to 1. And again, I don't want, this is like a homework, you read it, okay? Just I want you to know that you may see this in applications, and the correlation coefficients are always between -1 and 1. All right? You can actually define the covariance of two vector random variables. Nothing new now, similar definition to what we had before. So for the covariance of one vector x, right, we had this basically, where here we had x, but now if you want the covariance between x and y, you just plug in y there. So apart from that, things are the same. All right, so let me, I'm going to give you this little slide and then a plot to convince you that this correlation coefficient can be very confusing in practice. So let's say we have two random variables x and y, and we have some linear relation, and let's take the coefficient in one case to be positive and in another one to be negative. You can show that in this case the correlation coefficient, it is +1, okay? In this case with a less than 0, the correlation coefficient is -1. In general, you can show that the coefficient a is given like this, okay? I mentioned that independence implies that the variables are uncorrelated. Uncorrelated does not imply independence. And when the variables are correlated, you really capture only this type of correlations. Nothing more, okay? So here is, come on, I wanted to show you, okay, I jump a few slides to show you this picture from Kevin Murphy's machine learning book. This is really a very important diagram, basically showing to you how you can get confused with two random variables being or not uncorrelated by using this correlation coefficient. So let's start from the bottom, right? So every dot you see is basically realizations from two dimensional random variables, and obviously the relations between x and y, as you can see on the bottom, is nonlinear. We agree? So you know what? If you calculate the correlation coefficient for all of this case, it comes to be equal to 0. So immediately you're going to say, wow, they're uncorrelated. No, they're highly correlated, but the dependence here is nonlinear. Okay? Now, if you go in the second row, all of these are straight lines, and the correlation coefficient, you can say, look, this has slope 1. Yeah, but this doesn't have slope 1. But still the correlation coefficient is equal to 1. As a matter of fact, the correlation coefficient in this case, you know how much it is? because you remember the correlation coefficient is the covariance divided by sigma x, sigma y. In this case, sigma y equal to 0, so this is infinity. So the correlation coefficient in this case is infinity, right? But obviously you can see things are linear. And again, another bunch of data where effectively the correlation coefficient captures a little bit the nature of the linear relation, and if the slope is positive or negative, and also it represents the different values, how noisy or how much you depart from the linear relation. Okay, but in cases where the relation is nonlinear, the correlation coefficient doesn't do anything for you, which means it's a very bad measure to say something about the dependence between these two variables. Okay. What are we going to do in those cases? We will discuss this in the very near future. Okay, so I will spend another lecture to tell you on how we can deal with this. All right. I think I already have discussed this. Okay, maybe I should put this slide earlier. Actually, did we miss some slides before? There were some slides that we missed. All right, so let me see if there is anything important here. This slide actually it's important, and it may come up in your calculations, okay? Do you need any assumptions between x and y to write this equation, you think? The answer is no. Do you need any assumptions to write this? The answer is yes, they need to be uncorrelated. Of course, if they're independent, this will be also true. All right, so don't ever write this thing unless the variables are uncorrelated. This, however, is applicable regardless what. Okay, so with expectations, you can write this, but this requires uncorrelated random variables. I give you a nice example, and I'm not going to go through, but I strongly recommend that you do it. Okay, if I type something, all right, with my own little fingers, means must have some value. And the problem here is I'm taking x to be a uniform random variable, and I take y to be x squared. So obviously they're highly correlated, right? You give me x, I'll tell you what y is. So when I do the calculations, and you should do them, all right, and tell me if I did something wrong, the correlation coefficient in this case comes to be 0. And it goes back to what I told you, if the relation is nonlinear, you don't capture it with a correlation coefficient. Okay? The algebra is very simple, so please look at it as an example. So, so later I mentioned we will cover this in a forthcoming lecture. Possibly I may say something actually on the lecture on Thursday. The entity that is going to help us to address these nonlinearities and how variables are correlated is really mutual information. That would be a very good measure of variables being truly independent of each other. All right, so let me go back to things we already saw. If we have this joint probability density, we define marginals, all right? This is the sum rule that I mentioned before, okay? I can do the same thing for y. And now I am going to define, it's a new concept, we're going to define the conditional of the conditional probability density. You remember we defined conditional distributions for the probability of events. We haven't really said anything about densities. Of course, I said something in passing. If something looks, reasonable, most probably is correct. But we really haven't. I mean, these are not events, so this is not necessarily an obvious thing. But because it looks good, it has to be right. Okay. So you know how we prove it? I'm going to put the equation, if you tell me you understand how we prove it, from, we have proved this, we introduced this definition of conditional probabilities for events. So I want you to look here and tell me how from events I actually go to that equation there. So I leave you alone with that big equation and tell me if you follow the proof. If you do, I'm not going to say anything. this is a conditional probability that involves events, right? X being between A and B, and Y between gamma, Y minus epsilon, Y plus epsilon, where epsilon is timing. All right? So you follow the derivation, see how from events I can actually immediately discover here something that I baptized to be the conditional PDF. You see that? Yes, no? Right? This here that you see is by the definition of the conditional probability for events, right? You remember what was the definition? Here I have to put the joint, and here I have to put the probability of the Y event. So the joint, I use the definition of the joint density to represent that. The integration for X is going to be from A to B. For Y is going to be from Y minus epsilon to Y plus epsilon. And similarly, I have this in the denominator. Now, I integrate around Y, so really I can get rid of the integration of Y and put a 2 epsilon there. All right? So 2 epsilon cancel out, and I put this inside the integral because it doesn't affect. It is variable in Y, this is integration in X. And you can see I get the joint density of X and Y divided by the marginal of Y, and I call this the conditional density of X given Y. Okay? So basically, we're building this equation in terms of densities without any new definitions, right? Everything comes from the conditional probability for events. All right? So this joint distribution of P of X and Y, I can write it P of X given Y times P of Y given X times P of X. Okay? So in general, when you see little p, defines densities. If you see capital P, it's usually, we use it for probabilities of events. In many books, these densities are denoted with a Greek letter pi, not p. And I think maybe here and there in my notes, if you see instead of an English p, you see a Greek p, that's the same thing. And you know what? There is the Bayes rule, okay, that we have seen this for events, okay, and this actually would be our starting point when we work on Bayesian things, okay. So if, how do we go from this to this? Can somebody help me? It takes 2 steps. How do I go from this to this? So the first thing we do is what? We write this, the joint divided by P of Y, all right? And then instead of substituting this is what we use. We use now the symmetric term, P of Y given X times P of X, okay? So basically, this is how we're gonna do inference. If we try to compute X given some observations Y, we're gonna use a likelihood model because we know what Y is given X plus some prior on X, all right? And this would be a normalization factor. So this is literally Bayes' rule that we will spend weeks, if not at least a month or 2 to discuss later on in the course, but we're done. That's Bayes' rule. So if you're taking this course to see Bayes' rule, this is what the equation is in terms of densities. All right, so let me introduce now the conditional expectation of a random variable X given Y. I think I have done this in terms of events, maybe in the second lecture. So what you do here is, because you are given Y, instead of using the density of X, you use the density of X given Y. Okay, that's the only thing that changes basically in our definition. So you are looking for the expectation of X, but you say Y is given. So instead of having the density of X, you have the conditional density of X given Y. Okay? Now, this is extremely important because everything, when we do inference, right, some things are given, some things are unknown. So we're going to be playing with the expectations. And here is, let me give you the formula at the bottom. This is something that we will be using very often. If you want to find the expectation of x, but it's easier to compute the expectation of x given y, then effectively what you need to do is take this expectation of x given y and integrate it in y with p of y. And the proof is actually trivial. The proof is indicated in the two previous equations. And it's manipulation basically of probabilities. You agree this is the definition of the expectation of x, right? Nothing fancy. So what am I doing? I'm substituting now p of x with this big parenthesis or this integral. So what rule of probability do I use from here to there? How do we call that rule of probability? P of x to go to this integral. The sum rule, okay? We integrate y out. And then because we already have defined the conditional density, this can be written as p of x given y times p of y. And then, you know what I do? I change the order of integration. I integrate first in x and then in y. So I'm rearranging things like that. And what is this integral? By definition, is a conditional expectation of x given y times p of y, and we're done. And again, this equation, right, looks, if something looks nice, it has to be correct, okay? And so usually, that's why I always recommend to the students type equations in your homework, because if you write just like that, right, whatever, you cannot see if something looks nice, because it doesn't look nice. So I always say, if you don't write it clearly, it must be wrong, okay? And I stopped looking, actually. So when my students come and complain to me, but you haven't read it, you know, I gave you a report. It's like, sorry, it doesn't look good. And they ask me, what doesn't look good? And I say, visually. If visually looks good, it has to be right, okay? Now, I'm not writing the equation with a variance, because it may look visually not as appealing, okay? But it will actually be more useful quantity to play with, to use this for variances. So I'm going to come back to that in a future lecture. A little bit of a sort of parenthesis and appendix here. If we have two variables, x and y, that they are linearly dependent, so x and y here are vectors, A, so it's a matrix. The expectation of y, it basically follows this equation, A times the expectation of x plus b. But what I want you to remember, because you'll be using this often, the covariance of y involves A and A transpose, all right? So it's A covariance of x, A transpose. If you don't believe that that's the case, please use the definition for covariance of y, plug in this, and you will immediately come up with that result. Okay, so remember, A transpose, if the relation is linear. I am going to use this all the time, okay? And you can take a specific case of this when, you know, instead of a matrix, you have a vector, and y is scalar. So if y is a scalar, actually if y is a scalar, then b should not be bold, okay? So I need to, a mistake on slide 22, so this b should not be bold, right? Is this bold? No, okay, so that's correct at least. All right, multivariate Gaussian. So we have seen the Gaussian in 1D. So this is your famous Gaussian in what dimensions we have here? In D dimensions, okay? So you have this very nice quadratic exponential in here that is, you know, you have to keep in mind that sigma is, the covariance is symmetric and positive definite. Actually, in the computation of this quadratic, if sigma was not symmetric, it would make no difference, right? Because of the symmetries on this x transpose x, okay? But the fact that sigma is symmetric implies that we only need very few variables to describe it, all right? So it's not a full matrix. And this is the determinant of sigma. And here you have 2 pi to d over 2. So this whole thing here, it's a normalizing factor. Lots of times, you're going to have to calculate some integrals that involve this exponential dx, and you don't have to do any algebra because you will look at this and say, you know what, the integral of this whole thing is really 1 over this, because the density is normalized. All right, so the normalization factor will be very handy for a lot of calculations. And you will see this type of calculations coming up when we talk about Bayesian model selection later on in the course. All right, again, I have a nice equation for two independent Gaussians showing this linear transformation, so I'm going to bypass it. I think in your first homework, you're going to have to do some plots, and I'm not quite sure how much software the TAs have given you. You feel free to cut and paste. Even MATLAB has infinite toolboxes. Lots of these things, if they still work, you can download the software, change it, do anything you want to. But here what I have is I have two random variables, x and y. These are the equi-probability contours. You can see actually, if you want the contours where p of x is constant, really this quadratic thing here has to be constant, and those are ellipses, okay? And this is what you see here. Now, if you want a conditional probability to plot, so let's say if you want to fix x equal to 2, y equal to 2, effectively, you can take a slice of this joint distribution. This is what you're interested in, okay? So really, in unnormalized fashion, you can derive this directly from the joint by fixing y, okay? So this is p of x given y equal to 2. Now, p of x is to come up on p to p of x from p of x and y, means for every x, you're going to have to integrate all the y's out. Okay? So this is p of x, this is the conditional, and again, this shows you this, how you get it as one slice of the two-dimensional distribution, and this thing you have to integrate basically y out. All right, 107. How are we doing the slides? 35. You think we're going to reach the 50? How many I said? 60? All right, so there is hope. All right, there is hope. The next topic is extremely important and very confusing to students, okay? And very essential for playing with probabilities. So let's say we have two random variables, x and y, okay? These are the values they take, so I abuse a little bit the notation. And let's say that x is some function of y, any function. And I call this x g of y. So if somebody gives you the density of x, or let's say even easier looking at this, if somebody gives you the density of y and tells you, can you find what the density of x is? The thing you need to remember is that probability densities do not transform the way functions transform. So it's not like you take the density, let's say, of y, and then you substitute, for every y the corresponding x from, and say that's it. That's wrong. So you cannot just map densities the way you map functions. Why? Because as you go from x to y, what you preserve is probability mass. Okay? So really what you preserve is, you look at the neighborhood of dx, right? And p of x dx is the probability that you're around x in a very infinitesimal slice dx, okay? So what you want to do is, you want to take this probability and make it equal to p of y dy. You want to preserve probability mass, okay? And then if you look at this equation, immediately you can see of p of y is p of x times dx over dy, okay? And I'm using here absolute values, right? And I'm going to generalize this. But effectively, if you know the probability of x, to get the probability of y, you don't just go where you have x and you put x equal g of y and you say, that's my answer, wrong. You have to multiply this with the Jacobian dx over dy. Okay? And how will you remember this when you do calculations? This is how I remember it. P of x dx should be equal to P of y dy. Okay? This is extremely important. So probability densities do not transform as functions. Okay? Do not transform as functions. All right. The algebra shown here is trivial. There's nothing really. Okay. I got rid of this absolute value and I put the derivative of dx over dy is g prime of y, and I put an index s which is -1 or +1. Okay. And I have one example. Just to verify that we know what we're talking, and you can look at this in details. I said let's take the gamma distribution that follows this PDF, and let's use this to compute the PDF of y equal 1 over x. And because I already said something in an earlier lecture, if x follows a gamma distribution, 1 over x follows what distribution? Inverse gamma. So we better get the inverse gamma distribution if we do this correctly. So if you use the formula I gave you, all right, you compute px, instead of putting x there, you put g of y, which is, it's 1 over y, all right? So x is 1 over y. You calculate dx over dy, which is -1 over y squared, and there is the inverse gamma distribution, okay? If you actually don't use this, and you just plug in x equal 1 over y, that's the wrong answer, and you'll be suffering because nothing will be working in your computer program or in the algebra, and you'll be in trouble, okay? All right, how do you generalize this if x and y are vectors? So instead of using dx dy, basically you need the Jacobian of the transformation, which is the determinant of del x del y, and I actually give you the inverse of this looking here, but del x over del y depends what, if you know x is a function of y, y is a function of x, you either know this directly or the inverse of this, but is again p of x dx, p of y dy. It's easy to remember for multivariate variables, you just need the determinant there and an absolute value. And I give you another example that you should read. If somebody gives you, let's say, the probability of x and y, where these are like Cartesian coordinates, and you want to write this, the probability of r and theta in polar coordinates, you can actually, the only thing you need to do is transform first this, right? Put x equal r cosine theta or sine theta, and this is the determinant of the Jacobian there, which is, in this case, comes to be equal to r. All right, I want to say something about this picture because it talks about volumes. So let's say we have a distribution of p of x, all right? And as you notice there with the beams, really the way that I come up with this distribution, I take samples, right? And I plot a histogram, and that's my distribution p of x. So let's say that somehow you do a transformation, and you want to find the probability of y, where y is g minus 1 of x. All right, so this is my g minus 1 function, all right? And I want to actually map p of x to p of y, all right, through this function. Now, someone will say, oh, you know what? I can take each of these values, transform it like this, and come up with this nice curve that you see there. I don't know what color is that, orange, yellow. That's the wrong answer. The wrong answer is because you really haven't accounted for this Jacobian of the transformation. So if you actually work on this sample by sample, so if you take the sample, let's say you sample x, and you use the nonlinear transformation to find y, then you will come up with a histogram that you will see deviates from what you will conclude to be the answer by simply using this as a function and transforming it by y equal to g minus 1 of x. All right, so this is a nice picture that shows you don't transform distributions thinking of them as functions, because they are not functions, they are probabilities. Okay, and when you transform probabilities, what you need to remember is you need to preserve probability mass. Okay, p of y dy, p of x dx, and if you know that, you never do a mistake. All right. Now we're gonna do more algebra, right? So I can introduce you to distributions that are gonna be very fundamental for Bayesian analysis, but again, it's just algebra. I don't want you to remember anything. I want you to know where to find things, okay? Because these things, you cannot remember them overnight. It takes some time. So look at the equation on the top and tell me if we discussed that and what exactly did we discuss. I mentioned on how we get the student t distribution with fat tails. And so when I introduce this equation, so can somebody tell me exactly what we do here? We basically, a student t distribution, which will be the result of this integration, right? It's really an infinite sum of Gaussians, all right? For all possible precisions tau, where these precisions tau follow a gamma distribution. So you sum up a lot of Gaussians for all possible taus, where the taus follow some gamma distribution. When you do this calculation, you get a student t distribution that has fat tails. They don't go to zero the way the Gaussian does. Okay, and this is how we got the univariate student t distribution. Okay, and so what I'm going to do is now I'm going to take this equation that we introduced, and we discussed lots of things about the univariate student t distribution, and I'm going to rewrite this integral with a transformation of variables the way that you see here. So you have to believe me that if you use these transformations, so if you take, and you define eta to be some new variable, this is my variable tau. So if I define some new variable eta, that is tau times beta over A, if I define another variable lambda to be A over B, if I define nu to be 2 times alpha or A, you have to believe me that this equation is transformed to that. All right? Where here, instead of having a distribution or gamma distribution on tau, we have a gamma distribution on this new variable eta. So to go from here to there, you're going to have to transform this distribution from a distribution in tau to a distribution in eta. And to do that, you're going to have to use the Jacobian of this transformation, which is how much? So for example, this distribution, right, would be equal to this distribution times d eta divided by d tau. And what is d eta over d tau is b over a, and what is b over h? 1 over lambda. So you're going to have to change that. You're going to have to change the variable you're integrating. Here is tau. We're going to have to integrate on eta. So lots of things cancel out, and you get this nice formula. And you may say, who cares? Well, I care. If I tell you that, means there must be a reason we care. Because this very nice formula, okay, we are writing differently this definition of the univariate student t. This nice formula can be generalized to 3 dimensions. So look how you take something which is scalar, and now I'm extending it and say, let me define a distribution in d dimensions, all right? Where here, instead of lambda, I'm going to put some precision metrics and a multivariate Gaussian, and there I keep the same univariate gamma distribution. So basically, I don't change anything here. I keep whatever it was there. The only difference here is I go from a scalar Gaussian to a multivariate Gaussian, where I make mu to be a vector, and instead of scalar precision lambda, I use a matrix precision, because I'm making a multivariate Gaussian. Lambda, remember, is 1 over the covariance, okay? So this, you can generalize it, right? And it takes this form, and when you do the algebra, and the algebra is in the slides, you get this nice distribution, and this distribution is the multivariate student T distribution. And you say, and do I care? Yes, you care, because this, you know, when you start doing calculations, right, and you will see this in a Bayesian way, and you're trying somehow to get rid of this theta, you know, by putting some prior on it later on and integrating out, things lead to different, more complex distributions, and the student T distribution comes natural. Now, do I really care about all of these coefficients? Yeah. Because these coefficients, when it comes to model selection, everything will depend on these normalizing factors later on in a Bayesian setting. You don't have to remember what they are because they're in the books, they're in the slides. Just remember a nice distribution that comes from some averaging of many Gaussians, and it looks like this. And this quadratic delta square there, it's a new distance, right? That you know, you may use actually this in even when you play with data. This distance is called the Mahalanobis distance. Okay, so lots of people in machine learning, in statistics, they use it to compute distances between points, and you notice these distances are weighted with this precision matrix lambda. So there is a philosophy why you want to do this, okay? So a lot of times people use a diagonal lambda, etc., but this comes naturally here, okay? And it is a new distance generalizing basically the Euclidean distance that takes lambda to be equal to identity, but here you have this nice Mahalanobis distance. The proof is in this slide. Actually, you can literally see it. Some things that they are in blue or different colors are to help you to see where the substitutions take place. This actually performs this integration in 2 lines. Really, this is what you need, okay? And you can compute the mean, the mode, the covariance, so everything you want for the student T distribution. And again, if you do it in a smart way, if somebody tells you go and compute the mean of this, right? So you know what you will do? You multiply this by x times all of these complicated things dx, and you're going to try to integrate that. And that's the right way, but if you do this with a little trick, all right, the derivation for the mean is trivial. Please read the slides, okay? And if you do this for the covariance, actually it's also trivial because the only thing you need to do is the covariance of a Gaussian, okay? And the rest is basically nothing. So to compute the covariance of a student T distribution is literally 2 lines with a little trick where in the calculation you use the formula that the covariance you know, of a Gaussian is basically eta times lambda minus 1, right? This is the precision, so inverse of that would be the covariance. Unimportant things, okay? Bottom line, if you search on Wikipedia for the distribution, you can extract every property that may be of use to you. We're not going to be doing algebra by hand in this course, right, extensively, but I don't want you to worry and say, or wonder from where things come. They come from algebra, okay? And algebra generally is good for you to do it once, so you know that there's no magic, okay? All right. You remember something important that I stated for the univariate student T? What happened when the degrees of freedom of the distribution go to infinity? It becomes Gaussian. The same thing is true here, obviously, right? So you can actually show one line of calculation that you see here, that as nu goes to infinity, this thing becomes Gaussian. All right. So the student t distribution will be extremely important. And now, for Bayesian analysis, one more very complicated distribution, extremely important. You may even wonder how is this going to come in our analysis. For those who work especially on non-parametric statistics, the Dirichlet distribution and what's called the Dirichlet process are very important and sort of very up-to-date topic in machine learning. So we really need to discuss about this Dirichlet distribution that literally generalizes the beta distribution. Anybody remembers the beta distribution, how it was looking? It was x to alpha minus 1 times 1 minus x to beta minus 1. Okay. So here is the Dirichlet distribution, and it will look very weird, to start with. Okay, so imagine that we have k competing events. Okay, so we have k competing events. So this Dirichlet distribution gives you the probability of this capital K events to be mu k for each of them, given the fact that we have observed each of these events alpha k minus 1 times. I remind you that in the beta distribution, it was the probability of x being x to alpha minus 1, 1 minus x to beta minus 1. Here I'm looking at k events where each of them happens with probability mu k, and I'm looking in a distribution of the mu k's. All right? And obviously, if I have capital K events, all right, and the probability of each of these is mu1, mu2, etc., and I know that each of these events happen alpha 1 minus 1, alpha 2 minus 1, then the probability of mu given these coefficients alpha is what you see here. Okay? So the sum of these mu k's has to be equal to 1 because they are probabilities, but what I want to emphasize, this distribution is the probability of mu given the coefficients alpha. Okay? So that looks very weird, but when we will use this as a prior later on, things will click basically, and you will not have any issue sort of exactly what this is. That is the, it's the belief that the probabilities of these events are mu k, given that each event has been observed alpha k minus 1 time. Okay? So it looks weird right now, but think all the events have probabilities m1 to mk, and we also have the information that each of these events happen alpha k minus 1, so the joint probability distribution of the mu's has to be this. All right. Why is this distribution painful? Because the algebra is complicated. Okay? All important things, right, come with some pain to learn them. So the first thing you see is, because the mu k's have probabilities and their sum is equal to 1, really the dimensionality of this problem, you don't have capital K independent mu's, because for example, mu capital K can be written as 1 minus all the summation of all the other mu's. So really this is a distribution in K minus 1 space. So lots of times you will see it written with capital K variables, but it's really distribution in capital K minus 1 space. Okay? All right. So for example, if I plot this distribution in mu1, mu2, mu3 space, basically what I get is a plane, because mu3 is 1 minus mu1 minus mu2, or mu2 is 1 minus, mu3 minus mu1, so it is a plane, okay? The normalizing factor, again, you say who cares, but model selection will come and will tell us we really need to care about this a lot. Not for sampling methods, but for model selection. So the normalizing is this multinomial beta function, and the multinomial beta function is basically the product of gamma functions for each of the coefficients alpha k, divided by the gamma function where the argument is the summation of all the alpha k's. Okay? And you may say, I don't believe you. I don't believe you actually that if you integrate this, it's normalized. Well, if you don't believe me, I took the time to actually prove it in the notes so you can read it. Right? Because if I don't put in the notes and I give you a formula and say, oh, here is the Dirichlet distribution with lag, it's not going to be much of help. Now, if I do a lot of things, will it be of any help? I don't know. But I cannot sit you and say, here's this formula, good luck. Right? I have to give you things that you may find useful, if not today or tomorrow, maybe next year when you do this, you use this in your research. All right. We have a few minutes, so let's, we need to do some algebra that is going to be coming way down the road in the course, right? But it will come in very different settings, okay? So here what I have done is I have defined this normalizing coefficient as 1 over the beta functions, okay? It's nothing else, it's the inverse of that, really, okay? So here is one of the fundamental formulas that I'm deriving on this slide, okay? So let's start with the result. It says that the expectation of the log of mu j, remember the random variables here are the mu's. These are the, these are the probabilities that each of these little k events will happen. So they are random variables. So the expectation of each of the logs of each of these mu's, it comes out to be the d gamma function, I will define it shortly, corresponding to the coefficient alpha j, minus the d gamma function corresponding to the sum of alpha j's, which we denote as alpha 0. This calculation, trust me, it will be coming often, especially when you use variational methods and non-parametric statistics. So this is sort of very useful result. And what is the d gamma function? The d gamma function is nothing else but the derivative with respect to alpha j, or with respect to any argument, of the log of the gamma function. So this is the definition of psi of alpha j, and this is the definition of psi of alpha 0. Now, how complicated, I mean, when you look at this, right, it looks is like, wow, this is awful. My recommendation is take your pen, a piece of paper, and say, okay, wait a second, he wants to calculate this. What's the definition of the expectation? Take the actual distribution, which is this, right? That's my distribution. Put log of mu and do integration. That's what expectation is. And then what you need to do is you need to use some simple formula that says that the derivative of this product with respect to each of the alpha j's is log of mu j times this product. So if you do this, immediately you come up with the result on the bottom. So the algebra, it's not painful if you write it, if you type it actually, because if you write by hand, you will miss something here and there, but when you type it and you look right, it looks nice, right? It looks nice, okay? Bottom line, if you do research in this area, right, and you have to do any of these calculations and you trust what you read, the chances that you will do things wrongly are infinite. Because you will be trusting basically whatever you copy from here and there without knowing, is it really true? What does it mean? How do I program? But there's not much algebra. You do it once and then you're happy. So this is the expectation of log of mu j. It involves this d gamma function. You may ask me, and I'm not going to prove it, you may ask me, well, wait a second. You said here is this distribution. Can you prove for us that this distribution is actually normalized? Right? And an easy way to prove it, and I'm not going to go through this, is to prove this by induction. So for m equal to 2, if you have two variables only, it's the beta distribution, and we have shown in an earlier lecture that's normalized. What you need to do is assume that the distribution in m minus 1 variables is normalized, and then prove that this then has to be normalized on m variables. And if you do the algebra on 2 pages, you get the answer. Okay? So you don't have to worry, the distribution is normalized. Now, I am going to give you sort of a hint of where this distribution is going to be used. Remember that this, we will see it maybe 7, 8 lectures down the road, okay? So we're a little bit way ahead now, but there is nothing really new. Sort of you have the machinery to understand what I'm talking. So let me consider that I collect data from a multinomial distribution. Anybody remembers what's the multinomial distribution? It's a generalization of the coin experiment, right? So what is the multinomial distribution? And you can think, all right, I have this, capital K variables, right? And each of them is on with probability mu1 or mu2 or mu3, right? And I do lots of experiments. The first experiment, variable 2 is on. The second experiment, variable 1 is, and then again 2, and then variable 5. And let's say, when I do n experiments, I accumulate the variable 1 to be on m1 times, then the variable 2 m2 times. So this multinomial distribution was mu1 to power m1, mu2 to power m2, etc. So the likelihood, if my data come from a multinomial distribution, is the product of mu k to a power mk. That's the multinomial distribution. All right. Now, if you collect data from a multinomial distribution, you don't really know what the mean is of the multinomial distribution. So we wrote, the likelihood as the product of mu k's to the power mk, but we don't really know what this mu k is. So what we do is we use Bayes' rule, all right? And again, I'm going ahead 7 lectures now, but look at this equation without any understanding of what the prior is, what the likelihood is. Does this equation, what calculation in probability this reminds you? This is my data. So what is this calculation doing? So this is the likelihood of the data, right? Is what's the probability that I will observe this observations m1, m2, etc. if I knew the parameters, if I knew the mean of the distribution, right? And this is a marginal in mu, is what I call some prior information that I have on mu. This is what when we become Bayesian, we're going to call this a prior. But this product here, what does it remind you, this equation here? This is what? How do we call this rule of probability? The product rule. But now I give it a new interpretation, right? So this is the posterior. If I have observed the data, I'm asking, can I say something now about the parameters mu? And using the product rule, this is the likelihood that comes from a multinomial distribution. And as a prior, I take it mu to come from a Dirichlet distribution. And notice what happens. If you multiply the multinomial distribution, which was the product of mu k's to the power mk, and you take this to be Dirichlet, then the Dirichlet distribution is the product of mu k's to alpha k minus 1. So by a miracle, the posterior of mu comes to be what type of distribution? Dirichlet. And we call that actually, so another topic that we will cover, but it's in your homework 1, somehow by having a multinomial, then taking the prior to be a Dirichlet, it comes that the posterior is Dirichlet, and we call that prior to be conjugate, right? Because to the likelihood, because effectively the posterior has the same form as the prior. The only thing that is new is the coefficients have been updated from the prior coefficients to some posterior coefficients that involve these measurements nk. So you know what? I've gone way ahead of where we're supposed to be with this slide, right? So if you did not get it, it's okay, because we will do lots of little examples in further lectures. But really, it's the product of probability, and I said, make this a multinomial, look at the notes, what this is, make this a Dirichlet, and then what you get is another Dirichlet. This is nice. That's where actually the Dirichlet distribution is going to come to play a role in, at least in the early part of our calculations. So the posterior mu is a Dirichlet that has now these updated parameters, okay? And if you want to write it with the normalization factor, that's the nice answer. All right. I want to give you now plots, because obviously if you're going to use this as a prior, you may ask, and what parameters do I put? I have lots of parameters there, these alphas. What do they mean? Are they of any use? So I'm going to do this in 3 dimensions only. And in 3 dimensions, you only have 2 independent variables, right? mu1 and mu2, so we have really a triangular to plot this. So in the graphs on the top, I try to keep all the coefficients alpha k the same. So that way, what I'm really changing is their summation, alpha 0. And notice, if the indices are 1, 1, 1, I get a uniform distribution. Extremely important. So basically, if you want to have what is called an uninformed prior, you don't really want to bias things one way or another. This Dirichlet 1, 1, 1 gives you a uniform distribution. If you start increasing the alpha 0, so here for 2, 2, 2, you know, it is a broad distribution, but it's really centered around the center of the triangular. And if you make the strength even higher, it becomes narrower around the center. All right? So if you want to say, this is where you know, I want to be, basically you use a very high coefficient alpha 0. If you use all the coefficients to be less than 1, look what is going on. The only non-zero region for these probabilities is on the edges of the triangular. Okay, on the edges of the triangular. And if you want to say, well, I want to bias, so the only non-zero things are in this side or in that, then effectively what you need to do is play with the location of this alpha case. So if you put a 10, you get this is concentrated here, this is concentrated there, and you know, similarly you can, if you put the 10 on the front there, you will be concentrated in there. There are lots of different little programs you can run to actually see how you plot these distributions in 3 dimensions. And this is actually an even more important piece. And you know, we're going to be using this type of things later on, right? Suppose you have a Dirichlet distribution in 5 dimensions, you fix the parameters, and somebody says, can you give me a sample from this distribution? How do they look like? And you can see here, you remember when, let me just go back. For example, when this alpha k's are less than 1, right? All of the samples were concentrated on the edges. So you can see here, these are only a few samples, right? 5, so they are not necessarily representative, but if you look at carefully, you will notice you get these big samples where mu k is equal to 1 and everything else is 0. You get this mu1 at significant value. Once in a while you get something in the middle, but more or less the mu k's are concentrated on the edges of the distribution. If you take alpha equal to 5, these are representative samples. Okay, this is how they look like. Again, you don't have to memorize anything. When you need things, you say Dirichlet distribution Wikipedia, and then immediately it jumps. It gives you the expectations, it gives you the mode, it gives you the variance, it gives you the covariance between mu j and mu l. It gives you other practical simplifications depending on how you define these coefficients, all right? Et cetera, et cetera. All right, I think we will need to stop there because it's 1:45. So what we're going to do on Thursday, I'm going to finish some introductory topics, saying something about Monte Carlo methods, okay? The topic that we will cover later on. And I want to spend at least half an hour to discuss something about information theory. Like we talked about mutual information. So what is that, right? So we will talk a little bit about mutual information, and we'll see where that takes us. There is a homework. If you have any questions, email the TAs, email me, and we will try to help you, okay? So see you Thursday. You don't need me. You go and pick it up. Sarah is there. You can go and pick it up. Yeah.